So my name is Jonathan Moore. I've been with Exida for just over 3 years. My background is mainly automotive. I spent many happy years at Ford Motor Company, mostly looking at standards-based software development and in reliability engineering in the electronics group. And I've worked for a tier 1 supplier in the UK. I'm a UK national, but I've spent most of my working life in the US. So the tier 1 I worked for was a consulting and safety services, as well as other consulting services and testing provided to automotive industry, defense, and a few other sectors. I worked for a startup for a few years, and then most recently with Exida, and that's where I became a certified functional safety engineer. Some of the projects I've worked on, automating haul trucks there in northern Utah. That was the team that I led to do that. The McLaren in the middle there was doing winter testing just south of the Arctic Circle in Sweden, and that was the team I was a part of doing. I had a part of the software there, but that was the team doing the climate trials. And then there's various other vehicles that I've been lucky enough to get involved with doing automation. Exida is based around the world. The two key offices, one is where I'm at here in Pennsylvania. We're about 2 hours west of New York driving, and the other office is in Munich in Germany. And there's engineers in all of the locations shown on the map here. Many of those locations are closest industry related where those customers are. But more recently, of course, we've been doing a lot of work with the automotive supply chain, as well as people using those components as they apply increasing levels of automation to vehicles and engineering solutions towards automated driving. We're the market leader when it comes to device certifications. We did about twice as many certifications as all 3 TUVs combined. And in the case of Logic Solver, after about a 20-year head start, we do more of that now than the TUV. Cybersecurity is off the chart. We do about over 90% of the cybersecurity, industrial cybersecurity certifications now. And it was our 20th anniversary this year. The celebration was put on hold because of COVID, but here are some of the names of the organizations we work with. This is a book that you can buy a copy of on our website. I strongly recommend you do that. It's everything you need to know about state-of-the-art safety techniques, and in particular this one covers things the standards don't cover. There's techniques in there that are far superior to the standards, including how to deal with areas where the standards are just plain wrong. The authors have since recognized that, but of course standards evolve very slowly. So if you're just following standards, you're going to find a liability gap in that. State of the art is a long way behind, a long way ahead of what the standards describe today. There is a new edition of 61508 that's about to be released. That's being developed. It's not about to be released. In edition 3, so we're a couple of years away from hopefully correcting some of the mistakes in there. And the latest edition of the automotive standard 26262 was published earlier this year, but some of that is already out of date, particularly for semiconductor. Chapter 9 is what I'm going to be focusing on. There's material in there that guides the application of diagnostics, particularly to embedded electronics. And there's some stubborn areas of the world that still refuse to accept diagnostics and will only accept redundancy, but there's really not a lot that goes on these days. We have many papers that are published showing the statistical basis for the effectiveness of diagnostics, and in all cases you're going to find that the diagnostics are much easier to implement than redundancy. There's a lot more books on the website. If you're looking for a gentle introduction, Functional Safety for Managers is a good one. Not very technical, but it gives you a basic understanding of what's expected of you. The I guess the seminal publications by Exida are the Safety Equipment Reliability Handbooks and the Component Reliability Handbook. We don't publish those in printed form anymore. All of that data is now electronic and embedded into our tools and maintained up to date electronically. So I don't think there'll ever be another edition of that in printed form. And that represents about 400 billion hours of field failure rate data. So the largest single source for authoritative information on the parts you use for safety, the failure modes you can expect, the failure modes that actually happen in the real world, their distribution and their likelihood. And of course, we've got experience in dealing with those failure modes and how to make sure that they don't contribute to your failure rate. And what you'll find if you're an integrator is that the majority of the components you want to use have either already been assessed by Exida. The suppliers have been working with us long before you decide you want to use their parts. And if there isn't a part in there, we'll gladly assist with that, or more than likely we're going to be able to find a part that's sufficiently similar that you can use the failure rates from a similar product. Functional safety then, making sure product can be operated safely, reducing risks to a level that's broadly acceptable to society, and what we have to do is collect evidence and construct an argument to prove that we've done this. So we'll cover some definitions, we'll look at types of diagnostics, we'll look very briefly at what we do in FMEDA, some examples, and we'll talk about proof tests as part of this work. In 61508, we have this time interval that's specified. It's the diagnostic test interval, the interval between online tests to detect faults in a safety-related system that has a specified diagnostic coverage. It's not a lot of information in there, but the time it takes, worst case, to complete the automatic diagnostics needed to achieve the published detected failure rate. So the basic idea is that we have a failure rate. We have a failure rate of 10, and we run some tests, and we make the claim that the diagnostics are effective, and therefore we want to reduce our failure rate by the effectiveness of the diagnostics. So let's say we think the diagnostics are able to deal with 90% of the faults, and we prove that with a test. Then our diagnostic test interval is the time it takes to run that diagnostic or that set of tests if we want to claim that reduction in the failure rate. So if we've got a failure rate of 10 and we think the diagnostic is 90% effective, then we might publish a failure rate of 1 for that device. But we have to publish the diagnostic test interval, which has to be achieved in order for that failure rate to be valid. And of course, if the diagnostic test interval is larger than the demand interval, we've got to anticipate the fact that we might be in a fault state with a demand on our system and not realize it. 262 refined the definition somewhat. They specify fault reaction time. Here's a time diagram showing that. We've got some period of normal operation before the fault occurs. The time it takes to detect the fault is specified as the diagnostic test interval in 26262. Once we have detected a fault, we've got the possibility to react. The time it takes us to react and get to safe state is called the fault reaction time, and that hopefully gets us into a safe state. And it's at that point that we might end up with a hazard. So the overall time from fault to hazard is the fault tolerant time interval. Clearly, we want to get into the safe state prior to that, which means we have to estimate or predict the diagnostic test interval and the fault reaction time to prove that. In the edition this year, the 2018 edition, it was refined somewhat. The fault tolerant time interval was now specified, the minimum time span from the occurrence of a fault in an item to a possible occurrence of hazard event if the safety mechanisms are not activated. So it gets a little bit more involved here. Remember, in 26262, we're implicitly considering a driver. 61508 makes no assumption whatsoever. So if you look at the sections of those graphs there, without a safety mechanism is the state we're expected to consider for our hazard analysis. And we have a fault without a safety mechanism, we can expect malfunctioning behavior to result in a hazardous event. And that's the basic time interval there. If we put a safety mechanism in place, then we have to sum up all the diagnostic test time intervals. There may be just one diagnostic, but this graph at least suggests that we might want to think that we might be detecting the fault partway through a diagnostic, and there might be additional diagnostics that need to run to confirm that fault. So we've got some finite time to detect the fault, we've got the finite time to transition to the safe state, and once that transition is complete, obviously we hope we're in a safe state well ahead of the hazard arising. And then there's a third version of this in part one of the latest edition, which anticipates we might have emergency operation. So we might have to split that time interval we've got between the fault being detected and the safe state to actually implement some emergency operation. And again, we need to be understanding all of these time intervals in our designs. We're going to focus on the diagnostic time for this particular webinar. This is the basic, I guess, the fundamental problem we've got to solve. Time along the bottom, failure rate, or the probability of a failure when there is a demand on our system is the red line. And over a long period of time, we expect that failure rate to increase at a constant rate. So if we don't have a good systematic capability, we probably won't be able to make the argument that we've got a constant failure rate because we're still suffering from infant mortality. If we're not careful, we let our parts live in the field too long, and we start suffering from wear-out failures, which are again not constant. So we've got to deal with that during our operation and define the useful life of our devices, work on our systematic capability to get the random failures that occur due to infant mortality. We've got to drive those out of our design, select designs that will survive the useful life, and then we're going to be monitoring them. And typically we'll get a dangerous failure occur, and hopefully that gets detected by an automatic diagnostic, and that raises a warning flag for a repair team to come out. And what they do is they go straight up to the top there because they take the unit out of service. They might have to stop the operation, so we have a loss of availability in that time, and now they've got to repair it, and then they've got to restore the safety function to a repaired state, which essentially resets the system. So we go back down to the starting point there on the PFD average there for the failure rate, and over time we accumulate the failure rate. It increases over time, and obviously eventually it'll cross the threshold again, and it'll either be detected or worst case we actually fail to detect it and we're in an unsafe situation. So that's typically how we'll do a repair there. Of course, it's not desirable to take units out of operation if we can at all avoid that. Some problems just present themselves for a period of time and go away. And it's certainly better if we can just replace the components that are broken rather than having to recommission an entire system. If there was a fault on your vehicle and you had to send it back to the manufacturer for a full requalification, that probably wouldn't go down very well. So we think of a modified analysis looking at the impact of automatic diagnostics here. The derivation of this equation and what those terms mean is in the book. I don't propose to go through that today. There's plenty of webinars from Exida on that. But what we expect is to go up the failure rate there, and we're going to detect a dangerous failure with an automatic diagnostic and hopefully restore the operation successfully at the end of that with a shorter downtime. But crucially, we're not necessarily resetting the system by doing a full requalification to prove that there are no faults present. So the failure rate just continues going up as we continue to operate the system after a diagnostic has been dealt with. And you can, of course, decide whether you're going to shut down when you've got a detected failure. That's typically the default position that a manufacturer might take, is as soon as an automatic diagnostic triggered on a safety system, we're going to shut down, because shutdown is unconditionally safe. It's not always the thing you want to do, particularly in the area of robotics, and certainly in the area of highly automated vehicles. We certainly don't want to be shutting down the car when it's driving down the freeway at high speed. You may even want to consider this for your low-speed robots, because it's probably not great customer relations for your robot to fail in the middle of the grocery store and just stop there waiting to be repaired, creating a nuisance to everyone that's now got to walk around it. So sometimes you don't want the automatic shutdown. There are failure modes that you can have a failure, but you can continue your operation. You can maybe even continue a limp home and get it back to the charging area, or get it out of the way, and then prevent it from leaving on the next operating cycle. So that would be with an automatic shutdown. So with an automatic shutdown, there's some extra terms to consider. Without the shutdown, obviously the PFD average will be lower. The key variables in that are listed here. You, of course, have to have an understanding of how your product fails, what the failure modes are, the failure rates, and any diagnostic coverage from automatic diagnostics. Now, a lot of people don't have a 400 billion hour database with that access to that data, so they come to exida to get that information, and we'll certainly give you calibrated failure modes for your environment and your product, and help you quantify all of those terms there. The next parameter is the mission time, how long you're going to be running the machinery for. Obviously, the longer you run it, the more failure rate you accumulate over that time. And then your proof test intervals and effectiveness and duration, they can essentially assert that a failure mode is not present, so you can reset that probability of failure periodically. If you've got a long time between your proof test and it's not very effective and it takes a long time to do it, you're not going to get so much benefit than a proof test that you can arrange to happen more regularly, and maybe more effective proof test. The mean time to restore is an attribute of what the end user is doing with your system. Might take them 24 hours, might take them a week. In sort of nuclear systems, it might take several months in order to restore a system. So we've got to deal with the unavailability during that time. And if we take a system out of service, we've got to make sure that if we do want availability, that we've got a backup system that can operate safely while we're servicing the primary system. Redundancy is another thing you have control over. You can choose to make your designs more redundant. Of course, the drawback with redundancy is you have to think about common initiating events that can cause both redundant or all the redundant devices to fail simultaneously, and you're back to a single point of failure. And then finally, the operational maintenance capability. How good are your customers at maintaining records and actually following through on your maintenance? Now, the thing to bear in mind with these figures, these parameters here, is that only 2 of them are under your control. You can choose to use more reliable components or more diagnostics and think about more failure rates to deal with for item 1, and you can choose to add redundancy. You can choose to pay more money into your design, make it more costly by adding redundancy. The other attributes in yellow there are not under your control. A best practice might be that you make some recommendations to your end user in your safety manual. You may even be a bit more stringent than that and require that they share the records of these activities with you, to make sure they're following. But at the end of the day, you can't force these things on the end user unless you're going to put that into a contract, and if they didn't follow them, switch the system off, which typically you're not going to do with your customers. So the mission time, the proof test intervals, how effective it is, the mean time to restore, operational maintenance capability, none of that is under your control of a manufacturer. You may make some estimates based on a worst case, and you can certainly make some recommendations to your end users, but ultimately it's up to the end user to determine whether they're going to do this and whether they're going to use a trained individual. So we're going to focus on number one, because this is where the low-hanging fruit is, especially for embedded systems. There's two types of diagnostic that we think of, two general classes, and not a great deal amount of literature on this. I think it's probably only safety engineers that really think about this deeply. So the two types of diagnostic are a comparison between two channels or a test for reference information with one channel. So by comparison, we're going to be looking at input data or data in tables and doing calculations and looking at those calculations. And by reference, we might be looking at time intervals and levels of things and logical combinations. So if you imagine the by comparison is you've got to get your weighing scales out and compare A with B. If you think about COVID, typically the first responders will do is measure your temperature, because we know that temperature is a good indicator of what the body is doing, and they have a reference level for the body. Most people, their blood temperature is it sits within a very tight tolerance, and an elevated temperature or a reduced temperature is a good indication that the body is having to work hard to deal with infection. So they will bring out the calibrated thermometer from the pocket, or these days a digital one, and they'll take a spot check of your temperature to compare to a known reference for the typical variation for humans. So compared to reference, then you've got to have an absolute reference to know what's correct. There's thousands of variations of this. One that might be more familiar to you is if you're using an ADC to measure data coming into your embedded system, you might connect, you might overspecify that ADC to get you more channels than you actually need, so that you can tie some of those inputs to ground or a common reference voltage, and what you're going to do is a plausibility check to make sure that your measurement is between 0 and the reference voltage. That is good. That 2-point comparison is good up to the most significant bit, so you can diagnose bit errors in your ADC. If you've got a non-linear measurement, you might need more than 2 points. But again, ADCs are reasonably cheap, and finding ADCs with additional channels to do that is relatively straightforward. It hinges on an understanding of the underlying failures and confirming the references are sufficient to cover those. So your FMEA is going to be crucial in helping you identify opportunities for compared to reference type diagnostics. Semiconductors often use temperature. Signatures are another effective diagnostic. You could, for example, do a calculation in your big loop, gather up a chunk of data, run some metric on that, and check that average is within tolerance. A simple one might be to, if you happen to want to use floating point or even integer, is record the min and the max that those variables take. And if in development the min and max of your floating point is within a few thousand, and suddenly you're getting calculations that are 10 to the 20 or 10 to the 50, all of which are possible with floating point, you might want to say something must have gone wrong, because we don't expect our floating point numbers to be so big or so small, let's say. And then the Watchdog is a very famous form of comparison to reference diagnostic. It's a feature of the electronics design. The designer will add a feature that forces the hardware to reset unless certain conditions are met, and typically those conditions can only be met by software. So resetting the electronics often helps with faults, because the memory is reset, and that certainly clears any single event upsets, which are a big source of failure rate in embedded systems. So allowing the software to start again may allow some or all of the safety function to continue until the problem happens again. If it's time that accumulates a software problem, certainly a periodic reset will allow us to reset that counter, clear that memory, and provide some function again until we can understand what's causing it. So typically what you'll do is you'll count the number of resets and the reason for that reset to include in your monitoring, so you know how often they're occurring. And maybe you expect one reset periodically every week or every month, but if you suddenly get 10 resets in succession, quick succession, you might want to go to a different safe state where you don't keep on resetting indefinitely, because clearly something has gone wrong. The simple watchdog will just require the software to reset the timer circuit periodically. That'll be an upper limit on the time. Once the time is exceeded, if the software hasn't requested a reset, the hardware will force a reset. If the software hasn't requested a reset of the watchdog, the hardware will force a reset of the hardware. We can modify that to require the reset appear within a window, the sort of Goldilocks state, where if the software watchdog resets too quickly, we also trigger a reset, as well as if the software watchdog triggers too late. So we've got a window of plausibility now. We can't have hung software that stops and doesn't reset, nor can we have software that's not doing its job and completing too soon and resetting the watchdog too frequently. That would be a windowed watchdog. But if we make sure the timer used by the software and the hardware are different, then we also reduce the common cause initiating events that can cause both of these to fail in the same way. So if we have a clock that drifts and it's the same clock we use for software as well as the hardware watchdog, obviously we can go longer and longer as that clock drifts. And if we've got some time critical safety functions, our watchdog isn't going to help us with that. So if we can use a dissimilar time base, dissimilar clock, then we can get rid of many of the common cause events that can cause both clocks to fail in the same way. So that's the windowed watchdog. Compared to operating unit, then, is the other type of diagnostic. Historically, there haven't been the resources on microcontrollers to do this, but definitely we're seeing an uptick in people wanting to do this kind of work now. The size of data that you compare is crucial. If you compare two small numbers, it's probably not enough. Many people have now got access to microcontrollers that can calculate cryptographic signatures very quickly. And cryptographic signatures, of course, a very, very low collision rate compared to, say, a CRC. And we can put that signature across large amounts of data to give ourselves confidence that the data is as we expect. There's a number of ways of doing that. We could do that by feeding the outputs of 2 units into some hardware comparison. If we do that in hardware, the advantage is we can probably do that comparison with some very, very simple components which don't particularly affect the failure rate. We could also do cross comparison between one unit and the other. So we design our hardware and our software to anticipate that there's got to be some data exchange between the two to confirm each other's operation. And we're at liberty to decide what that data is, of course. The drawback, of course, is that if we only have one sensor and both units are reading that same value from that same sensor, that's a weakness in this situation, because we won't be able to discriminate between a fault due to a faulty sensor, but certainly faults that affect one unit and not the other will always get detected. And if you want to Google dual core lockstep, that's a great technique that's used with microprocessors. And every clock cycle, the outputs of the CPU are compared with a second CPU, and we can get very, very high levels of diagnostic coverage there. Compared to operating unit, then, can be extended to more than one unit. The aerospace industry uses this a lot because it's expensive. But what this allows you to do is improve your availability, because now if 2 units agree, then presumably you can identify and isolate the unit that's in a fault state and continue operation, which, if you want to fly an aeroplane, is obviously fairly important to make sure that you can land. In automotive, typically there's redundancies not used. What they'll do is they'll have a diagnostic to do the comparison, and if there is a redundant unit, it'll simply be there to provide a limp home or some additional availability. It won't be used for redundancy. So we still see this in some places. There's either a good reason for it, or the people who are doing it don't know any better. If you're using triple redundancy, come and talk to us, because there's lots of opportunities to get the cost down there for you, potentially. So if the comparison block's big enough, then a 99% effective diagnostic is easily demonstrated. What that means is that your failure rate for those blocks that are protected by comparison will go down by 99%. That's a great value to you, and might assist you with your risk reduction. So if you can do the comparison every scan, then your goal might be to never get bad data that isn't detected, and that would certainly give you high levels of diagnostic coverage. But often the comparison takes longer than the time of an individual scan. If the system can't tolerate bad data for a period, then we must calculate the diagnostic time interval for each comparison to reference, and an exida FMEDA will always report the DTI. It's worth checking whether your FMEDA authors do that, and if not, you do well to ask them why. If the demand interval is 2 years, then it doesn't really matter if the diagnostic time interval is 24 hours. But if you've got a machine where the stopping distance is 10 meters and you've got a stopping speed of 7 meters per second, then we may need to speed up the comparison, because obviously every second that passes that we start approaching an obstacle takes away from our stopping distance and changes the stopping distance and the scan range we have to assert is clear of obstacles. So when we conduct an FMEDA, any diagnostic that doesn't execute within the cycle or within the time limit is not given credit, and that will be something worth checking in your FMEDA. Single event upsets is the largest source of random failures in a modern microcontroller. Typically, you'll find that soft errors are of the order of 2 fits per kilobit. So if you work that mathematics through, you'll find for 128K, you've got to deal with 2,000 fits, which will typically push you well above your budget for failure rate. But there's some very easy to do effective diagnostics there. CRC or cryptographic signature on your fixed memory. You can do reasonability checks. These are all things that are fairly straightforward to do in software to check that stored values are reasonable when you reload them. And everywhere else you could do double store. You could invert there if you wanted as well. And of course you could look at things like error correcting memories, and you could think about what you're going to do for single bits and double bits, and have the memory report faults so that you can either refresh the memory or reset or go into a safe state. So lots of options there to deal with that high failure rate. And I think it's not without coincidence that a lot of research money has been spent sending probes to the sun recently. The geometries that we're looking at now in 7 and 5 nanometer, they're incredibly small, are affected by high energy particles from the sun, and the desire is to fit even more silicon and even more transistors into our devices. So it's not without coincidence that we're going to go and study better what the sun is doing. I presume, hopefully, to be able to reuse that to improve our integrated circuits as they get smaller. The next thing I'm going to show you a couple of examples. So just a thought experiment, really. This problem comes up very often. You've got 2 forward-facing sensors that senses a distance. There's typically an overlap between those sensors, and typically they report angle and range. And the first step as a safety engineer is we need to start anticipating the failure modes and think about what diagnostics we can implement. So I'll give you a second to think about some potential failure modes. What failure modes can you anticipate here? Typically, we'd do a functional FMEA, a functional failure. We'd identify the functional failure modes using an FMEA. So the obvious ones is the LiDAR hasn't switched on, it's been kicked, and so it's now pointing into the sky, so we'll never see an obstacle. We could also have a unit that misleads us by giving us a wrong angle or a wrong range measurement. And the question then to ask is, how do we know these faults have occurred? Because if we know they've occurred, we know that there's an impact on our safety function, and we've got the opportunity to do something about it. So we might solve that by scanning part of our vehicle, part of ourselves. We could put 2 targets on the frame there. So instead of having a narrow scan range, we could scan right back on ourselves and across to the other LiDAR, put 2 targets on there, and clearly we should get a response there from that every sweep, and that will allow us to check the range and the angle, because we know what that distance is and we know what angle we expect those markers to be at, those fixed positions on the vehicle frame. And if they don't appear there, then either they've been moved or we've been moved, and we want to raise a concern there. Now, there's a number of variations that you could do on that. For instance, you could move the measurement position to middle there, so LiDAR 1 and 2 could both get a reading off the same measurement point. You could offset it so that LiDAR 1 always gives a shorter measurement to LiDAR 2. And if we put LiDAR 2 on there, obviously we could get 4 measurements now, 2 from the rear and 2 from the front. And if we made all 4 of those measurements different, that would also allow us to detect whether LiDAR 1 and LiDAR 2 have been swapped, because we've got some so the values are different and they're off center, so we know which is left and which is right. So lots of opportunities within that. And it's an exercise you might consider to think about that overlapping region. If you're going to send the vehicle back to a common point, typically for refueling, then that's definitely a best practice, because now you can see the refueling location arrive, and you know exactly what signature that should give your LiDARs. So you can potentially do an automatic test every time you arrive or leave the refueling location, whether that's charging or gasoline. For remote diagnostics, again, another situation that comes up regularly, particularly with automated vehicles. We've got a safety rated controller that is receiving our sensor inputs and controlling our speed. Maybe it's controlling our braking, maybe it's also controlling steering. And what we're going to do is we're going to hand off that sensor data to a high level system where we've got no safety argument. But what we want to do is make sure the high level system is functioning, because it might be desirable to switch off if the high level system has lost its head. So what failure modes can we anticipate there? Well, periodically what we could do is we could send a request to the high level system to process some sensor data. So we could send some real data, which might be the normal condition, but because we own that sensor data, we could have some fake sensor data in a table, and we could send that at startup or periodically. We could send some data that we know has to be computationally intensive to process on the high level system side. But again, we would have a reference there that we could compare. So we could send the data to the high level system and say, process this, give us the answer, and we could check that answer with some pre-known values or some pre-known ranges for that to make sure the high level system is doing its job. And if it's not, then we might use that as a decision to slow down or to shut down if we need it. We can extend that somewhat to look at the proof test. A proof test is a test that requires a human check whether it's failed or passed, and typically the human has to initiate that and then assert a pass before they release the machine for the operation. It's not preferred because as soon as we do that, we have to check the proof test coverage and take the human into account. And of course, humans are notoriously unreliable. The probability of error there is quite high. Unless you can do things, but you'd have to go to great lengths to make an argument that human error isn't a factor. Organisations like NASA, of course, might be capable of doing that. certainly aerospace thinks about pilot error, maintenance and tech error, and they put in place some fairly rigorous procedures to deal with that, not least training. But if we could arrange a periodic test that doesn't require the human to check, that would be an automatic diagnostic. And the more frequent we can do that, the more helpful it is to reducing our probability of failure. The winning solution here seems to be to use the refueling location as a plausibility check that all the sensors are doing their job. So you have some unique obstacles around your machine, maybe different heights that can get scanned, things that are too high, too low. Another strategy is you have the human press a button and the machine doesn't move until the human has walked around the machine, and again triggered all of the sensors to prove that there was an obstacle. So they've got 30 seconds to walk around the machine, and you've got to see each of the sensors trigger in turn as a proof test. So there are ways that you can close the loop on your proof test to improve your confidence that that test has been run and has passed. So that's the end of the presentation, really. I covered the definitions, types of diagnostics, what we expect in FMEDA, a couple of examples, and the proof test. We've got training coming up. Well, we've got training courses that you can take on demand. This is a list of all the training courses that are available on demand. If you want to listen to me, then I've got videos of me delivering the AUT 211 and 214 at the bottom there. And it's my colleagues that deliver the other classes there, but they're quite easy to listen to videos. If you pay attention and can pass the exam, then we'll give you a certificate for completing the videos. We'll also give you a certificate for completing the exam as well, and that's accessible online on demand. And there's some instructor-led training. That's not quite like these seminars. You can actually interact with us if you want and see us. But these are classes coming up in January and February next year, and into March. Yeah, we've got the first quarter set up there for you. The website is where you can find out more about these. This training will be online on YouTube for you to look at again. But the website's available for you. That's how to get in contact with Exida, and that's how to get in contact with me. So if you've got any questions, now's the time to type them in. Otherwise, I'll be glad to get an email from you. And if I can give you an answer in a few minutes, I will. If it's going to take me a few days to give you an answer, then I might come talking to you about a consulting activity to help you with a particular project. So please get in touch. For those of you on the East Coast, drive safely if you're going out. And oh, there's a question. Hi, how to apply to the online test? Yeah, so the online test is offered at the end of every training course. So if you want to take the online test and get the functional safety practitioner or the cybersecurity practitioner certificate, then you take the class, and at the end of the videos, when you've watched them all, you get a link to do the online test. And if you want to do the Certified Functional Safety Expert, which is again another test-based thing, there's an application form to fill in, and I don't think we're offering that online. I'm pretty sure that's an in-person test still, but that's another option available to you. Thanks, Cameron. Right, we'll leave it there if there's no more questions. 5 seconds for questions. Okay, well, enjoy the rest of your day or morning or whatever time zone it is with you, and hope to see you again on one of these webinars. Thanks very much.